Hello there, I'm Mark McCormick and I'm going to talk you through and demonstrate my 20 credit 4th year project, which was ChessBaxter. As the name suggests, the goal and requirements of this project were fairly simple. Design a system that allows Baxter the robot here to play chess against a human opponent. The system ended up having two main parts. The first was a computer vision system using images taken by the Kinect sensor here to detect the state of the board, such as where pieces are, what pieces are on the board, which is then used to inform moves via a chess engine for Baxter to make. And that's the second system, Baxter physically making those chess moves. The final system is fairly robust. The vision system is very reliable. It always gets the correct state of the board, but it is very slow in doing so. One of the main problems and constraints with the final system. It takes about 1.5 minutes to generate a classification of the board. At best, if a piece is taken, it's doubled, and it's a robust system, so if errors occur, it detects them and tries again, so it can go on for a while. The longest I've seen is 8 minutes to classify the board. As such, it's not very... it takes a while to play a game of chess against Baxter at the moment. But there was no time to improve that in this project. The second system, the Baxter movement system, is also robust. It has about a 15% error rate, so roughly 1 in 6 moves will require human correction. This is pretty good considering the small size of the pieces in chess squares, so it's fine motor control that's being used by Baxter, which is hard to get accurate, and there are just inherent noise in Baxter's arm. So I'll start by talking through the Baxter movement system because it's the simplest. It was implemented last without much time because the bulk of the project was spent trying to create a good enough chessboard detection system. It consists of a static mapping between Baxter right arm positions and board square positions. And I'll just start it up and talk you through it. So for this demonstration, Baxter is going to play himself. You can see the gripper being used. Baxter first moves to the position above the square of the piece being moved, moves onto the square of the piece being moved, closes the gripper to collect the piece, moves back up, moves across to above the piece, the square the piece is being moved to, moves down, opens the gripper and goes back up, and returns to base position. So because there's mappings between arm positions in every square in the board, this allows Baxter to move any piece between any squares on the board. There are some special cases and difficulties which are handled, like castling and piece taking, which is handled in conjunction with the chess engine. And the corner squares here are quite far for Baxter to reach. They end up being picked up at an angle, so they fall over when they put down another squares. To fix this pivot point here is used that allows Baxter to put pieces going to or from those squares down and adjust his arm position so he doesn't drop the pieces, which helps reduce the error rate. Okay, I'll just leave this running so you can see it working. The moves for Baxter to make are informed by the computer vision system. This works by having images taken from the Kinect sensor. The board in that image is then detected with using a SIF detector and image homography, which is a reliable system. It always detects the board in this angle and position. With the board detected, a TensorFlow inception classifier model is then used to identify what pieces are where in the board. So this works by well, firstly, the TensorFlow inception model was chosen because last year this project was done and it was found that traditional techniques like SVM, logistic regression, KNN, and etc., with feature descriptors like HOG and SIFT and ORB weren't very effective, and deep learning with TensorFlow Inception was. The TensorFlow Inception model is a image classification model which is pre-trained and released by Google to recognize 1,000 image classes from the ImageNet database, but it can be retrained with transfer learning to identify new classes. So it was retrained to classify 13 different classes, 6 piece types of 2 colors for 12, and empty squares for 13. With this model, it doesn't identify positionally, just the content. So to generate positions, the sliding window technique was used. This involved taking a 100 by 100 window, sliding it across the board image, and classifying the contents of it at each point. The output from each classification was then added to a heat map, and heat map peaks could be used to identify what pieces were over which square on the board. So if I show you a heat map over here, for the starting board position, which is this, a heat map looks like this for the Black King. So each piece type has a different heat map. As you can see, the heat map peaks here where the colours are bright, and this corresponds pretty well to where the Black King actually is in the image. The final model is pretty good. The Black Knight is a bit noisy, as you can see. There's some peaks everywhere in the image. Black Pawn is pretty good, solid line of pawns on front of the Black King. And so you can hear that here you can see the empty square is pretty good. Creating a good enough TensorFlow Inception model to generate good heat maps was the main challenge of this project. A lot of the pieces are very similar to each other and pretty small, and so from certain angles from the camera it can be hard to classify the differences. So a number of different models were trained and tried. There was a mistake in Baxter, which is incorrect, and this was the main challenge of the course, of the, I think that should be the nightmare of the project. With a good enough TensorFlow Inception model, the heat map data was used to label the board squares in the image, which are detected by the board classification system. This proved to not quite be good enough because the TensorFlow Inception model heat maps weren't quite perfect. So to improve the system and get it to the one which is used in the final system, which is reliable, more and more board state awareness was added. This started with piece count, so for example there should only ever be one king of each type, and so it didn't classify more than one of them. That improved the accuracy, and after that was done, it still wasn't quite good enough, so board state awareness was added. So for example, in the starting state, which was known because of the chess engine, there's a pawn in this place that can move to this square or this square legally. So each of these 3 squares was scaled in the heat map data for pawns, for black pawns specifically. This allows the board labeling system to properly identify which pieces in each square, and because potential squares are also scaled, it can detect which move the user has made as well. So this board state awareness means the game has to be played from starting position, which isn't too much of a constraint, and it leads to a very accurate system. So with that's really a quick overview of the entire system. It's described in more detail, of course, in the dissertation, but yeah, I think that's everything, so I'll wrap up here.